Good day to all of you. Again, my name is Michael C. Pasis from Mapua University, and welcome to my online electrical engineering review and tutorial channel. And today we will discuss another interesting topic on AC circuits, which is more on complex power in AC circuits or alternating current circuits. Now, to those who are new, please don't forget to subscribe on the subscribe button so that you can have a notification bell if there is a new video on my channel for additional information and refresher. And one more thing is you can have a thumbs up or like. You can share it with your friends in Facebook or subscribe. And today is our lecture for the fundamentals of complex power, which is as I mentioned, a very vital fundamental for computing the overall power in an AC circuit. Okay. Also, you can also visit some of the former lectures that I have on some of the links that on all of the videos that I already made, so that for refresher purpose. Okay, now what is complex power? So complex power, the unit is in terms of volt ampere. So if you can still recall what we have discussed on DC circuits, on DC circuits the power is only I squared R V squared over R, or simply whatever the voltage times the current. And that is in terms of magnitude. However, in this case, we are considering now phasors. So there is a complex entity. So it can be a phasor or a vector, or in terms of complex, which has a real and imaginary part. So complex power is the product of voltage and current, but in terms of the corresponding vector. When I say vector, there is a magnitude and there is already a direction part. So if we do that in an equation form, so we have this overall equation, which is very analogous to complex impedance, that we can multiply the voltage by the current, but you need to conjugate the current, okay, in order to have an angle which is the displacement of the voltage and current, and they must be differed by a certain angle, by a certain value. So you need to subtract the angle of voltage and current. So that's why there's a conjugate. Or simply, if we multiply this one, you have the complex entity in terms of PT and QT. So this PT here is so-called real power, and this Q in terms of total is your reactive power. And then your S is the so-called complex power or apparent power. The unit is volt ampere. So the real power is in terms of watts. The reactive power, which is Q, is their reactive power, which is in terms of volt ampere. Okay, reactive, volt ampere reactive, or var. Or simply, in other words, you can also have this in terms of the corresponding vector. The S here that has a bar, it means it is magnitude, and the angle here is in terms of degrees. So this theta here, which is I already described on complex impedance, is your power factor angle, which is the difference between the voltage and the current. Or simply, in other words, you can use the Euler identity that you have your S here, you multiply it by cosine and J sine, which is the imaginary part, then you can now get P and Q respectively in other forms. Or in other words, we can get the real power here by having the real part. So this is your real part, and this is your imaginary part. So the real part is of your S is S bar, means magnitude, times the cosine theta. And please take note that the theta here is the power factor angle, which is the difference between the voltage and current. You can also deal with this in the reactive power, which is the imaginary part of your S. Okay, this must be S, not Q. Okay, imaginary part of your apparent power S. So that is S times sine theta, or simply S times sine theta, theta b minus theta I, which is the angle displacement of your power factor. Okay, now we will discuss more on the complex power triangles on the next slide. Hello once again. So we are on our next topic on the basic fundamentals of powers in AC circuits. So one thing that you need to know is these triangles here, which is very, very important on some of the applications on AC circuit analysis. So I call this the complex power and impedance triangles. So you have two types of triangles which is dependent on power and impedance. Okay, let us go first to power triangle. So the power triangle is in terms of powers, in terms of three quantities. We have the S, the Q, and the P. As we have discussed on the previous slides or previous lessons, that S is apparent power, Q is reactive power, P is the real power, and the angle is the power factor angle, or simply, in other words, your angle theta here is the difference between the voltage and current angles. Okay. Now, by using, this is a right triangle, by using Pythagorean theorem, we can get some parameters which is very, very important in terms of the angle theta. Okay, first of which is the cosine theta, which is simply P all over S. So, in this case, the cosine theta here is your so-called power factor. That is your cosine theta S. Now, if you use the sine angle, which is your Q reactive power all over S. So, Q all over S sine theta, this is called a reactive factor. And last but not the least, is the tangent angle theta. So as you can see, that is Q all over P. So that is so-called a quality factor. So those trigonometric identities of cosine, sine, and tangent theta have its corresponding definition in terms of the triangle. So please be reminded of that. And one more thing, some of the equations here are derived already in terms of magnitude. So this is in terms of magnitude, by the way. All of the parameters here is in terms of magnitude because, as you can see, the S, Q, and P has its corresponding magnitudes. Okay, so if you do the complex number for S, okay, that is simply equal to P plus and minus JQ. Okay, this is already looks fun to you because this is the equation from the last slide, or simply in terms of magnitude alone, you can do this equation as well. So from that triangle, you can do many things. And from there, we develop the important formulas, okay, for power. Now, let's go further to the impedance triangle. So you have the Z, X, and R. Please take note that the P here is the horizontal here, the R is the horizontal, the Q is the vertical line, which is also your X or reactive component. So the Z here is the total impedance in magnitude, R is the resistance, X is total reactance or the total reactive component, and theta, as usual, is the power factor angle. So again, the power factor, which is your cosine theta, okay, I could abbreviate this as PF, is R all over Z, and please take note, all of the parameters here are magnitude alone, which is based on the units of your Z, X, and R. Sine theta reactive factor, I could say RF, and tangent theta, I could say QF, or quality factor respectively. So if you do the same pattern for S here, this is already looks fun to you. So Z simply equal to R plus or minus JX. And then you have here S squared, no? Or rather, Z squared is equal to R squared plus X squared in magnitude only. So this magnitude alone. So we can develop many formulas here. And why it is plus or minus here, it simply because it can be a reactive or reactive component or a reactor or a reactance component. So it means capacitive or inductive component. So it can be inductive or capacitive power. So it depends why it is plus or minus. So we already read and we just vibrate it that the line here is in the positive side. So you can have positive if that is the line is in purely capacitive, which is on the downward side. So you can have negative. So all of these are very important parameters, and we already developed the majority of the formulas for S and Z. By the way, one important thing that you must know, okay, that the angle here, which is theta S, and this is theta Z, and please take note, those angles are the same with the power factor angle, which is theta S is also theta Z, which is equal to theta, which is the difference between the voltage and the current angles. Now, we can now proceed to the formulas for AC power. Hello and good day to all of you. So let's move on to the complex power formulas. As we have mentioned on the last few slides, that we can have the apparent power S in terms of complex and polar representation, and we also discuss a little bit of the power triangles. So here, just a brief recap, we have here S is equal to P plus minus JQ, and we have here that that is also equal to the phasor voltage multiplied by the phasor current, but it must be in terms of conjugate. Now the question is why we need to conjugate. Okay, let us have a brief example here. So when you say voltage phasor, that is theta V, and V with the magnitude, then you have your I, you have your theta I. Now that comprise or compose of your S, and then you need to multiply. Now it's clear that the VI here is the magnitude of your S, but here theta V, if you multiply based on rules on phasor, you need to add, okay, the angles. So if you do so, if you have the same angle, which is in terms of positive, and you did not conjugate it, you cannot get the difference between the angles of voltage and current, wherein we already discussed all throughout that it must be theta V minus theta I. So in this case, you need to conjugate this one in order to have this relationship, wherein that is your power factor angle. So that's the meaning of that. You can conjugate the current, you can conjugate the voltage, but it depends. You can also have V conjugate I, but here we will use our default as V conjugate I instead of V conjugate I. So VI conjugate rather. You need to have that in a VI conjugate. Okay, the other formula is straightforward. You can get the S in I squared times Z. So the Z here, please take note, you must have an arrow sign, or V squared all over Z conjugate with an arrow sign means a phasor. Please take note that the I here and the V, which is squared, are magnitudes. So it will do the same thing for P and Q. Now, since S is a vector, so you need to have a vector in the impedance. While P, I squared R or V squared over R from DC, and Q or reactive power, I squared X per phase, or simply equal to V per phase squared all over X phase. So all of the powers here, no, power formulas is being presented. Now, we can now move forward to the problem solving of this topic. Hello, and once again. So today we will discuss a new topic for AC circuits, and we are under the topic of series parallel resonance under the lesson 3 or AC circuits. So let us first define what is resonance, and then after that we can discuss the series and parallel resonance. So let us have a definition of what is a resonance. So resonance is a type of circuit wherein the input voltage and current will be in terms or they are in phase with each other, or other way around. The current will tends to be in phase with the voltage. So what's the meaning of this? It means, okay, in terms of phasor diagram, the voltage and the current will be in phase with each other. So for this, the angle or the power factor angle is 0 degree. As we have mentioned before, okay, if they are the same, okay, or in phase with each other, the angle tends to be 0 degree. So it means that the circuit tends to be purely resistive one. So also, this is the meaning of the second definition, that the circuit tends to be purely resistive because the voltage and current tends to be in phase. And one more thing, resonance circuits, one application are tuning circuits. Tuning circuits. So when you say a circuit is being tuned, so it means it already go into resonance. If circuit input power, or rather the circuit tends to have the voltage and current will be in phase or purely resistance to be resistive, it means the circuit will go to resonance. So in this case, to become a purely resistive component, your reactive components must be null or zero. So it means that the total in a series combination, that the total reactance must be zero, or in other way around, in parallels, the susceptive or the susceptance must be in 0 as well. So these are the characteristics of a series resonance. But again, there is a deeper discussion about resonance in series or in parallel. We will make another lesson about that, another video. But for now, since this is a review, this is just a refresher, I just enumerate the characteristic of series or a parallel resonance. Okay, in a series resonance, well, as usual, the current is always in phase with the voltage. Number 2, the current is maximum. Number 3, the total impedance is minimum, or the circuit tends to be purely resistive. Number 4, in order to have a total XT, so if you can still recall, okay, on our equation, that XT or total reactance is XL minus XC. In order to XT to become 0, you need to have XLN equal, it must be equal to XC. So the power factor is equal to 1. The angle will become 0 because the voltage and current are in phase with each other. Since XL is equal to XC, so you can have 2 pi FL equal to 2 pi FC. So the F here can be regarded as a oscillating frequency, resonant frequency. So you can get the F here in terms of the equal sign of the XL and XC. So in that case, we can now get this relationship. So FO is equal to FR is equal to 1 all over 2 pi square root of LC. So this is Lux-Pam on your basic resonance. And then the current resonance, or rather the series resonance, is like a voltage magnifier. So this is analogous also to what we have discussed on circuits, that if you have a series that is concentrated in voltage, you have the current, you're concentrated in parallel. So this is a voltage magnifier. So the voltage at the inductor equal to the voltage at the capacitor, simply equal to, okay, this is what we have discussed so far in the power triangle, that is the quality factor. And then you multiply it by the voltage of the source, which is VL. So quality factor is equal to tangent theta, or in other words, in your circuit, that is the reactive component all over the resistive component. So we will go to the parallel resonance. Hello once again. So let us continue our discussion on the basic fundamental, especially to the series parallel resonance. We are under the parallel resonance characteristics. So this is the same thing with the series, and we have the head-to-head matchup in terms of numbers. Okay, so in parallel number 1, the current is also in phase with the voltage. However, when you say number 2, the current is in minimum. Unlike in the series, the current is maximum. So number 3, the total impedance is in maximum in a purely resistive relationship of your resonance. So the total impedance, can be computed using this equation, R squared plus XL squared all over RL. By the way, the RL here is the resistance of the coil. Okay, XL is the inductance of the coil. Okay. Next, number 4. Since in series you have XL is equal to XC, well here, in a parallel resonance, this will be different. XL over RL squared plus XL squared is equal to 1 all over XC. And the power factor is equal to 1. The angle displacement is also 0 degree. And if you substitute XL 2 pi FRL rather, and XC is equal to 1 over 2 pi FRC, on equation number 4, then if you simplify all of the things here using a little bit of algebra, you can have the oscillating frequency equal to resonant frequency, which is equal to 1 all over 2 pi square root of 1 all over LC minus RF squared over L squared. So all of the formula that is in the box is very important. So if you have the time, jot it down. And last but not the least, in a parallel circuit, it is a current magnifier, so you can get the IL equal to IC, or the inductor current and capacitive current, which is equal to quality factor times the source current. Now we can now solve the problems on resonance.